Have you ever looked at something like a copper pot and then maybe a silver ring and just wondered what really makes them different? I mean, sure, one's reddish, the other's gray, but what's going on at the most fundamental level? Today, we're going to peel back the layers on the mystery of matter itself.
So, let's take copper and silver. We use them for a lot of the same stuff. Jewelry, bowls, and they're both fantastic at conducting heat and electricity. But even with all that in common, they look completely different. And then you throw zinc into the mix, which kind of looks more like silver, but it's brittle and not nearly as good a conductor. So what's the secret rulebook that these materials are following?
And that really gets us to the core question here. How can two materials be so similar in some ways, and yet so different in others? To figure this out, we need to think smaller, like much smaller.
All right, so our first step is to break these materials down to their absolute simplest ingredients. See, most things we run into every day are mixtures, but materials like copper and silver, they're special.
They're what scientists call pure substances. And all that means is you can't just physically separate them into different bits. A hunk of pure copper is copper all the way through, and it always has the same specific properties, like that unique color and density.
So, what happens if you take a pure substance and try to break it down even more, this time using chemistry? Well, sometimes you just hit a wall. And when you hit that wall, you found an element. Elements are the ultimate building blocks of matter. You just can't break them down into anything simpler.
So how many of these fundamental building blocks are there? Right now, we know of 118. And that's it. Everything, and I mean everything, in the entire universe, from your phone to your body to the most distant stars, is made from some combination of these 118 elements.
Okay, so we've got our elements. But what gives each one its own unique personality? To figure that out, we have to zoom in again, all the way down to the smallest possible piece of an element.
And here we are, at the atom. An atom is the tiniest possible unit that still has all the chemical properties of its element. A single atom of copper is what makes copper, well, copper. All of its unique traits are born right here at the atomic level.
And here's a really key idea: consistency. An atom of an element is the same no matter where you find it. So an iron atom that crash-landed here on a meteorite is totally identical to an iron atom we mine from the deep ocean. They are fundamentally the same thing.
Just to give you a sense of scale here, which is pretty much impossible to really imagine, get this. If you could somehow blow up matter so that a single atom was just big enough to see, your own body would stretch all the way from Philadelphia to Miami. That's how unbelievably tiny they are.
Okay, so we have 118 different kinds of atoms, which make up 118 different elements. For the early scientists, this was like being handed a giant box of mysterious Legos with no instructions. The next logical step, of course, was to try and organize them. And as they studied them, they started noticing patterns, almost like families of elements. They saw that gold and silver were both shiny and easy to shape. Iron and copper were great for making strong tools. And then there were these weird ones like sodium and potassium, both super soft metals that went absolutely crazy if you put them in water. There was clearly some kind of order hiding on all that chaos.
But that's the million-dollar question, isn't it? With all these different properties, color, density, how they react, how in the world do you organize 118 unique building blocks in a way that actually makes sense?
Well, it took a lot of work from a lot of brilliant people, but they finally cracked the code. They created an elemental roadmap, and it's honestly one of the most powerful tools in all of science.
The solution is this beautiful, elegant chart, the periodic table of elements. And trust me, it's so much more than just a list. It's a map that shows us the hidden relationships between every single known element in the universe.
So how does it work? Well, it's actually genius in its simplicity. First, everything is arranged by its atomic number. That's just the number of protons in an atom's core. As you read across the rows, called periods, that number goes up. But the real magic is in the columns, which are called groups. Elements stacked in the same group share similar chemical properties.
Each little box on the table gives you the vital stats for an element. So if we look at our old friend copper, we see its name, its unique symbol, Cu in this case, and its atomic number, 29.
And hey, here's a little fun fact for you. Ever wonder why silver is Ag or gold is Au? Well, some symbols are obvious, right? Like H for hydrogen. But a lot of them come from their old Latin names. Gold was aurum, silver was argentum,
and lead was plumbum, which, funnily enough, is where we get the word plumbing. It's like a little piece of history baked right into the science.
Okay, we've got all the tools we need now. Let's bring this all the way back around and finally solve our original mystery about copper and silver.
And here it is, the big reveal. Look at where they are on the table. Copper and silver, even though they have totally different atomic numbers, are both in group 11. That's it. That's why they act so alike. They're in the same chemical family. Meanwhile, zinc, which is right next door with atomic number 30, is in a different family, group 12. Its location on the map tells us it's going to have different properties, and it absolutely does.
So, here's the bottom line. All of an element's properties come directly from its atomic structure. And the periodic table is the ultimate cheat sheet because it organizes everything by that very structure. This allows us not just to understand their behavior, but to even predict it. In fact, early versions of the table had gaps which let scientists predict the existence and even the properties of elements that hadn't even been discovered yet. How cool is that?
And that just leaves us with this one final amazing thought. The periodic table isn't just a stuffy old chart of what we already know. It's a living map for discovery. If this single table organizes the fundamental building blocks of our entire reality, what new materials, new technologies, and new wonders are still out there, just waiting for us to find them?